Okay, so today we're going to be starting our new unit over thermodynamics. Thermodynamics is the study of heat and how it relates to other physical quantities. Some of the things we're going to be talking about in this unit are things like heat, temperature. We're going to cover some of the laws of thermodynamics later on. Methods of heat transfer, that should be pretty simple. And then how heat affects an object's temperature. We'll talk about things like specific heat capacity later on. Okay, so just to review, everything on this slide should be information that you already are aware of. You should know that all objects are made of atoms or combinations of atoms. If it's a combination of atoms, we call those molecules, and that the atoms are in motion. And we'll see that on a simulation here in just a minute. Objects can exist in different states of matter. There's three common ones: solids, liquids, and gases, depending on how these atoms or molecules are formed and grouped together. There are other states of matter that we're not going to talk about, but those are the three most common. And so what we're going to do is we're going to take what we've learned in the past units about energy and the things you should already know that are on the slide, and we're going to build upon them to gain an understanding of things like heat, thermal energy, and temperature. Okay, so please follow along, take good notes as you go. So the first thing we're going to do is we're going to look at a simulation I have, and we're going to look at answering some of these questions. Okay, so on the simulation, we have a container, and it is a cell container, and these little blue dots here are atoms, individual atoms. I can change the type of atoms they are. Right now they are neon atoms. I could do argon atoms if I want. I could do water molecules. If you look closely, you'll see these are not atoms, but they're molecules because they're kind of grouped in bits of two. Or not water molecules, oxygen molecules. And these are water molecules. Again, you can see the individual atoms are in there, but they're kind of moving as groups of three, two hydrogens and one oxygen, because water is H2O. So just for simplicity, I think we're going to look at the neon atoms first, just because they're a little easier to see. Right here we have a solid. Notice that what's characteristic in a solid is that the atoms are kind of neatly arranged together. They're compacted. They're not floating around. They're not really free to move. They're kind of held tightly together. But even though they're held tightly together, notice what are the atoms doing? They're moving, right? They're kind of vibrating, jiggling in place, if you will. And so I would say from the last unit we learned about things like kinetic energy, where kinetic energy is energy of motion. And so I would say these atoms have a lot of kinetic energy, or not a lot of kinetic energy, but they definitely have some kinetic energy because they are in fact in motion. Here is a liquid, and we can see how the atoms are rearranged differently in a liquid. They're still kind of held together. Every now and again you'll see individual atoms kind of floating off and doing their own thing, but for the most part they're kind of held together, but they are kind of free to move around each other while still being held together more or less in a group. Again, you'll see some individual atoms floating over here. That's because when you have a liquid, above the surface of a liquid, you typically have a few kind of stray atoms floating above the surface of a liquid, and we call that vapor. And then here we have a gas, and in a gas, the atoms in a gas are all kind of broken apart from each other. They're not really interacting with each other aside from colliding with each other. For the most part, they're all free to move and bounce off of each other, bounce off the container walls, etc. Okay, so those are the three states of matter. Now, if we take a look at a solid, going back to the solid neon, notice up here I have a thermometer. Right now it's reading 14 K. Now the K is for Kelvin. The Kelvin is the scientific unit for temperature. We can also do Celsius. What you do not see on this list is Fahrenheit, which in the United States we use Fahrenheit as our temperature scale, but most other countries use Celsius or centigrade. So if you go travel in other countries, especially like in European countries, whenever they have the weather channel on and they're talking about the temperature, typically the temperature is measured in Celsius. Okay, so typically we're going to work in Kelvin or Celsius in this class, but again, there are two units measuring the same thing, that is the temperature. So what does that mean the temperature. So now what we're going to look at is trying to figure out what is temperature actually telling us exactly. And the way we're going to go about that is I'm going to cool down the solid neon thing. And as I cool it down, we're going to see the temperature is going to decrease. And I want you to closely watch the atoms, the neon atoms, and see what changes as I cool them down. Okay, so right now you can see up there the temperature is decreasing. How would you describe the motion of the atoms now? Is that 1 Kelvin now? And now it's 0 Kelvin. Okay. Let's see that one more time. I'm going to slowly heat it up a few degrees Kelvin. Okay, take a look at the motion of the atoms, the individual atoms, not the whole blob of atoms. I realize the whole blob of atoms just kind of bounced off the bottom of the container. Ignore that. Look at the motion of the individual little atoms in there. Okay, and now I'm going to cool them down again. Watch how the motion of the individual atoms change. Okay, and then we're back at 0 Kelvin. Okay, so I want you to take a minute, think about what you just saw, and try to answer these two questions. Number one, as I decreased the temperature of the solid, how did the motion of each individual atom change? And then two, when I get to 0 Kelvin, how would you describe the motion of the atoms now when I'm at 0 Kelvin? This is called absolute zero, by the way. 0 Kelvin is called absolute zero. How would you describe the motion of those two atoms? So try to answer those two questions. Okay, so now we're going to slowly heat up the atoms. And again, ignore the fact that the whole blob just kind of bounced off the bottom there. Notice as I increase the temperature, hopefully what you should have realized is that as you decrease the temperature, the motion of each individual atom slows down, right? As I cooled it down, as I decrease the temperature, the individual atoms begin to move more slowly, and then when they reach 0 Kelvin, which is absolute zero, right, they stop moving completely. Now what you should see as I'm increasing the temperature, notice I'm at 31 Kelvin now. It's already become kind of like a liquid. It was a solid before. And if you look at the motion of each individual atom, they're vibrating faster, they're shaking faster, they're moving faster, they have more kinetic energy. And as I continue to increase the temperature even more, it goes from being a liquid to a gas. And if you keep looking at the individual atoms, and you look at how they're moving, how would you describe their motion, you should be able to easily see that they're moving faster and faster and faster. As the temperature increases, the individual atoms begin to move faster. In other words, the kinetic energy of each individual atom is increasing. And now it's already, 155 Kelvin, 156 Kelvin, and I definitely have a neon gas right here, and the atoms are all flying around and hitting each other. Okay, so using that simulation, we should be able to answer some of these questions we had before. What do you notice about the motion of the atoms at 0 Kelvin? Again, this is called absolute zero. And the reason it's called absolute zero is because it is absolutely the lowest possible temperature an object can have. Okay, by definition, 0 Kelvin, absolute zero, is the lowest temperature an object can have because the atoms stop moving at that temperature. Okay, they have no more kinetic energy at that temperature. And hopefully you saw that in the simulation. Now, in real life, it's not possible to actually reach 0 Kelvin, but theoretically, if you could reach 0 Kelvin, that would be the temperature at which all atomic motion stops. As you heat the atoms, what type of energy are you adding? Hopefully you saw as we added heat, as we increased the temperature of the object, you should notice the individual atoms are moving faster. And in the last unit, we learned that energy of motion is called kinetic energy. Okay, and so what type of energy are you adding as you heat the atoms? So to speak, you're adding kinetic energy, the kinetic energy of the individual atoms. As the temperature of the atoms increase, how does their motion change? Obviously, they move faster. Okay, so let's talk about some definitions. If you just pause here and read over what it says about thermal energy and heat, this might be something good to add into your notes. So here's what it says in the notes. It says thermal energy. What is thermal energy? Thermal energy is the total, keyword there is total, energy arising from the kinetic energy of its individual atoms, molecules, and ions. Okay, so what does that mean? Well, that means let's say you have a container with, I don't know, 100 atoms. Okay, each individual atom has kinetic energy because each individual atom is moving. And if you're moving, you have kinetic energy, like we learned in the last unit. Okay, so thermal energy you would find by finding the energy from each atom, the kinetic energy from each atom in a container and adding each of those energies up. Okay, so that's what it means by the total energy. Okay, it just literally means the sum of the energy, the sum of the kinetic energy of each individual atom, molecule, and ion in an object. Okay, so clearly, the faster these atoms are moving, the more thermal energy that object has. If an object has more atoms, it has more thermal energy, right? Because that would mean you're adding more things. So if I have 2 atoms, I don't know what object has 2 atoms, but if I had 2 atoms, I would be adding the kinetic energy of 2 atoms together, right? I would be adding 2 numbers together. If I had, let's say, 1,000,000 atoms in an object, I would be adding 1,000,000 numbers together. And so clearly, the more atoms you have, the more thermal energy you have, and the faster they're moving, right, because kinetic energy is energy of motion, the more thermal energy that an object has. So what is heat? Heat is the transfer, and again, that's the key word there, transfer of thermal energy from one object to another. So what is the difference between temperature and these other words? So here is the definition of temperature. Okay, take a look. It's in the first bullet point here. It says temperature is a number that measures the average kinetic energy of the atoms or molecules in an object. And I want you to underline the word number. Temperature is not measured in units of energy. Temperature is not energy. It is a number that represents energy, but it is not energy itself. Okay, so temperature is a number that measures the average kinetic energy of the atoms or molecules in an object. So what is the difference between temperature and thermal energy? If you look at the definition for thermal energy, this has a word total in it. Temperature has a word average in it. Okay, that's not the same thing. So when you find the total, you add up a bunch of numbers. When you find the average, you add up a bunch of numbers and then divide by the amount that you added up. Okay, so in other words, let's say you had 100 atoms. The thermal energy would be the kinetic energy of each atom added together. The temperature is not equal to the average kinetic energy of the atoms or molecules, but is a number that measures the average kinetic energy of the atoms or molecules. You would basically find by taking all of those energies and then dividing by 100. Okay, so that is the difference between temperature and thermal energy. So in the picture to the right, how can the 2 cups of water have the same temperature but different amounts of thermal energy? Okay, if they have the same temperature, by definition, they have the same average kinetic energy in their molecules. So how is it possible that this one has more thermal energy? Well, if you look at the definition of thermal energy, it's a very simple question. This one has more thermal energy because it has more atoms, right? Or in this case, it has more water molecules, but it has more atoms, and that's why it has more thermal energy. Okay, so temperature, thermal energy are kind of related concepts, but they're not the same thing. And these are the 3 temperature scales that are the most common to see. You do need to know some key facts on here. Basically, you need to know everything that's on the slide. You do need to know that 0 Kelvin is absolute 0. You do need to know why that's called absolute 0, because it's the temperature at which all kinetic energy, all kinetic motion in the atoms stops inside an object. And you also need to kind of know some other things. For example, you don't really need to know anything about Fahrenheit. Fahrenheit is just kind of here, so you have like a reference point to gauge from. Mainly you're going to see problems in Celsius and Kelvin. So 0 Kelvin is negative 273.15 degrees Celsius, right? They're equivalent temperatures. So that means if 0 Kelvin is the lowest possible temperature, that also means that you cannot have a temperature below negative 273.15 degrees Celsius. Two other things you need to know. The Celsius temperature scale, the way it's defined, the freezing point of water is defined as 0 degrees Celsius. The boiling point of water is defined as 100 degrees Celsius. Now, if you compare that to Fahrenheit, which we use in the United States, 32 degrees Fahrenheit is the freezing point of water, and 212 degrees is the boiling point of water in Fahrenheit. I don't know about you, but me personally, I kind of think the Celsius scale makes more sense, but for reasons that we're not going to get into, we don't use Celsius in the United States, even though most other countries do. Okay, so make sure you understand those two definitions about Celsius. They are up here in the notes section of the slide. Okay, so we're going to skip some of this. Okay, this is just a review slide. We talked about this before. Just because two objects have the same temperature does not mean that both contain the same amount of thermal energy. So for example, we have lead, we have tree sap. Same temperature, meaning by definition the atoms have the same average kinetic energy, right? Because they have the same temperature of 75 degrees Celsius. But the tree sap has more thermal energy. And we kind of talked about this before. How could that be? Well, remember that thermal energy does have to do with the kinetic energy of the atoms, but it also has to do with how many atoms you have. Okay, so clearly the tree sap, if they have the same temperature as the lead, the atoms have the same average amount of kinetic energy. The only reason the tree sap would have more thermal energy is if there's more atoms in the tree sap. Okay, and that's kind of what it says on the next slide. Okay, just a few more slides. So when two objects are able to transfer thermal energy between them, we say they are in thermal contact. And basically, the slide asks what are some examples. There's lots of examples of this. I mean, if you put an ice cube in a cup of water, those two objects are in thermal contact. If you're sitting in a room and the room is cold and you feel cold sitting in the cold room, you're in thermal contact with the air inside that room. Okay, if you jump inside the swimming pool, then you would be in thermal contact with the swimming pool. Okay, so thermal contact just means that two objects are able to transfer heat between them. Now, here's what tends to happen if you have two objects in thermal contact. Okay, this whole bullet point is important. It says when two objects are in thermal contact, heat will flow from the hotter object to the colder object until they reach thermal equilibrium. Thermal equilibrium is in bold because that is a vocabulary term. The terminology thermal equilibrium is a condition where you have two objects in thermal contact, there is no net heat flow between them, and they have reached the same temperature. Okay, so in other words, let's say it's hot outside, the temperature of my skin is 100 degrees because it's hot outside. I go inside where there's air conditioning, and let's say it's like 75 degrees. If I sit inside long enough, the temperature on my body is going to cool down to be the same temperature as the temperature in the room. Okay, so if I wait long enough, I'm going to reach thermal equilibrium with the room. Here's another example. If I take let's say a spoon and I put it in a pot of boiling water. Now, boiling water has a temperature of 100 degrees Celsius. Okay, if I throw the spoon in the water, let's say the spoon is originally at room temperature. Over time, if enough time passes, the spoon is going to reach thermal equilibrium with the water. In other words, the spoon is also going to reach a temperature of 100 degrees Celsius. Okay, because in thermal equilibrium, two objects have the same temperature and there's no net heat flow between them. Okay, and then I think the last thing we're going to talk about just really quickly is pressure. Pressure you only have with a gas, and it tells you on this slide what pressure is. It says the pressure of a gas is a number that measures how frequently, that means how often, the gas particles collide with their container walls. So what we're going to see is number one, we're going to verify that that's true, and number two, we're going to look at what are some ways that you can actually change the pressure of a gas. So going back to our simulation really quickly, here we have a container with some atoms in it. There's a gauge up here that shows us the pressure. We're going to stick with the neon for now. Now, watch what happens as I heat up this container with the neon atoms. Notice there's no pressure right now. And the reason there's no pressure, I'm going to pause it for a second. The reason there's no pressure is because you only have pressure in a gas. Now, what you're going to see over the next few seconds is as these individual atoms start to come off of the liquid and become a gas, as they collide with the walls of the container, each time there's a collision, this pressure gauge is going to increase. And so what I want you to see is that pressure is a measure of the frequency, or how often the atoms of a gas collide with your container walls. Okay, so we'll see that as I increase the temperature a little bit more. As they start to collide, notice the pressure is increasing. ATM, by the way, is atmosphere. That's the standard unit for pressure, or one of the units for pressure. You might also be familiar with PSI, or pounds per square inch. Okay, so notice every time there's a collision, this number kind of shoots up. As I increase the temperature, remember temperature is a measure of the average kinetic energy of the atoms or molecules making up an object. As I increase the temperature, the individual atoms move faster. Now, if the individual atoms move faster, that also means that the gas particles are going to hit the container walls more often. Okay, that's just kind of logically speaking. If they're moving faster, that they're going to bounce more often against the walls. And you can see that temperature is going up, pressure is also going up. Okay, now the last thing we're going to talk about today is what are some other ways you could increase the pressure of a gas besides increasing the temperature. Okay, so pause for a minute and think about that. Okay, so here are the other ways you could increase the pressure of a gas. Number one, you can decrease the volume of a gas. Now, if you decrease the volume of a gas, what's going to happen is because the atoms have less space to move around in, they're going to bounce off of each other more often. Okay, therefore, by definition, the pressure of the gas is going to increase. Okay, and you can see that. Number two, if I add more gas atoms, again, just based off of the definition of pressure, pressure has to do with the frequency of collisions with the container walls. Well, if I have more atoms, clearly I'm going to have more collisions. Again, that's just kind of common sense. Okay, so those are the three ways that you can increase the pressure of a gas, either by increasing the temperature of the gas, decreasing the volume the gas is stored in, or adding more gas atoms. Okay, and clearly you can see if I increase the pressure too much, then bad things happen and things explode. Okay, so just to kind of summarize, we're going to leave off on this slide right here. It's kind of a summary of most of the things we've talked about. The only thing that's not on this slide is thermal equilibrium. Okay, so using your notes that you have access to, go ahead and write out the definition of thermal equilibrium, and then we will pick up in the next video.